Hello, this is MA280 Multivariable Calculus. I'm Professor Wheatley. Today's topic, we talked about the dot product last time, one way of multiplying two vectors together. Today it is the cross product, the other way of doing it. Okay, so reminder, the dot product resulted in a scalar, not a vector. It's a scalar product. Scalar was the result of it. Okay? The cross product is another method of vector multiplication. And it should come as no surprise to us. This time we're going to get a vector as the response, not a scalar. So the results in a vector, and as such, it's sometimes called the vector product also. Okay? Okay, here's how it goes. So two vectors uv in space, both non-zero. We're going to see in the next section that if u and v are not parallel, then they will determine a plane. So if u and v are not parallel, they determine a plane. All right. Let's draw this up here. So here's a vector u, here's a vector v. They're non-parallel. All right. We'll draw a plane around them. So there we go. Okay. What you want to do now is you want to choose a unit vector n, which is normal, or perpendicular is another synonym for normal. We talk about vectors being normal to a plane versus perpendicular to them, but they mean the same thing. Normal to a plane, normal to the plane by what we refer to as the right-hand rule. All right? So here is the angle between u and v. And notice I'm being careful here to draw this from u to v, because it does make a difference which way I draw it in. So what does the right-hand rule say? It asks the question, which way does the thumb point on the right hand when the fingers are curled through theta from u to v. There's a mouthful. So the right-hand rule says this. It asks you, take your right hand and look at the way that the angle curls. It's curling counterclockwise around the circle from u to v. So if I curl my fingers counterclockwise through the angle from u to v, my thumb points up. Right? If I were to curl the other way, in other words, if the angle were to go clockwise, right, have my hand like this, I would curl it clockwise, thumb would point down. So which way does this vector point? Well, the vector points up and out of the plane. Right? So there's n. As you can see this here, so let's draw this in as best as possible. Let's try this again here. So that doesn't look very good. How about, there we go, yeah. And so there's your right angle. This vector n is at a right angle to both the vectors u and v and the plane defined by them. Okay? So the vector n is normal to this plane. It's at a right angle to the plane defined by u and v. Okay? All right. So what does that have to do with the cross product? Well, definition. So once you have your vectors and your plane and your normal vector, can define the cross product. So the cross product of u and v, and I'll denote that with an x in the middle rather than a dot. So there's the x, not the dot, and this is read as u cross v, okay, is, and at first it'll look clunky. It's going to be the length of u times the length of v times sine theta, theta being the angle between u and v, going from u to v, times n. In other words, this is some scalar, and so the cross product is going to be a scalar multiple of n, right? So u cross v is a scalar multiple of n, and as a consequence, since n is orthogonal to both u and v, so will the cross product be, right? So u cross v is orthogonal to both u and v, right? Well, why is this nice? Well, think about it this way. We learned a method in the dot product section for expressing a particular vector as a sum of two things which are orthogonal to each other. Now we have a method of obtaining, for any two vectors, a third vector which is orthogonal to both those two vectors. Okay? Also, it's worth noting, too, that this only applies to 3 space, not to 2 space. There's no idea of a vector being perpendicular to vectors in 2 space. So it kind of goes without saying, but this only applies in 3 space. Right? Okay, so let's look at another idea about this. So we solve it with a dot product. 2 vectors were orthogonal if and only if their dot product was 0. Well, a similar definition exists for the cross product. So here, non-zero vectors u and v are parallel if and only if, where am I here? The cross product is 0. Excuse me, yeah. Right? And notice, again, this is the 0 vector, not the scalar 0. This is a vector product. And that should make sense because 2 parallel vectors don't determine a plane. There's no normal vector out of that you know of. If they're non-parallel, they determine a plane. There is a normal vector. So let's check this out for a minute. So remember, this is if and only if, so it's a 2-way road here. All right? So u and v are parallel. I'm going to use the double-sided arrow here to indicate if and only if. Double-sided arrow indicates if and only if. Well, 2 vectors are parallel if they have the same or opposite directions. That means the angle between them is going to either be 0 or pi, depending on which way they're going. If they're going the same way, it's 0. Opposite ways, it's pi, right? So the angle between them is equal to 0 or theta is equal to pi, all right? And in that case, for either one of those angles, 0 or pi, the sine of theta is equal to 0. And as a consequence, this whole scalar zeroes out. And so we have 0 times the vector n. That's the 0 vector. So let me include that out. So 0 times n will give you the 0 vector. So there's your if and only if statement on that. Okay? All right. Look at some properties of cross products. Here's where things get a little bit different from dot products and other multiplication. Dot product, other than not being associative, behaved essentially as multiplication did for real numbers. The cross product has a couple issues with it. So, properties of cross products. Let's just clean this up here. properties of cross product. All right. Well, if you have some scalars multiplying by your vectors, some r and some f multiplied by vectors u and v, well, things behave nicely here. The scalars just distribute. They look like that for any scalars r and s. Right? So scalar multiplication stays the same, no problems there. Okay? And cross products are distributive over plus u cross w. So for any vectors v plus w, you cross it with u, the cross product does distribute. And the same is true if you put it the other direction. So if you had v plus w cross u, you had this on the outside like that, that would be v cross u plus w cross u, right? So in some sense, so distributive over addition in some sense, but here, so the next one's a big deal though, because at first it seems like these are the same thing, but they're not, because this is not a commutative operation. So suppose we flip this around and we ask, what about v cross u? Is it the same as u cross v? Well, it's not, no, it's the negative. And the intuition here is the following. So remember, I said before that as your hand curls through the angle direction matters. Your thumb points up, or else if it's the other way, your thumb points down. If I'm flipping the order of the cross product, I'm flipping the direction of the angle, counterclockwise to clockwise. I'm flipping the direction of the normal vector. Okay, so that's why you have a negative out front. All right, so it's non-commutative. Non-commutative. All right. And we have the degenerate one down here, that if you cross anything with the zero vector, you still get the zero vector. Okay, no big surprise there. What's important to note, though, is that in general, and the proof here is somewhat involved, we're not going to do it, but in general, associativity here fails. Associativity failed for the dot product because it gave us some degenerate statement. It gave us a scalar dot a vector. It's not what happens here. I mean, everything is vectors here, but in general, these are not associative. So generally not associative. Okay. All right. So those are the properties. Now comes the important part. How do we get these things? How do we calculate cross products? All right. So let's get this off of here. So calculating cross products. Okay, so what we need to do here is take about 2 minutes and go back and talk about matrices again for a minute. So recall. If you have an n by n square matrix, right, then it has a determinant. Okay? And in particular, we care about the 3 by 3 case especially, because you can't do these things for 2 by 2 case. There's a thing as a cross product in 2 by 2. And higher dimensions we don't really care much about either, but we do care about these things in 3 space. So we care about the 3 by 3 case. All right, so let's remind ourselves what these things are, determinants. So here's a 2 by 2 matrix, A. It has entries A, B, C, and D. Remember that the determinant of A, det A, determinant of A, which I'll also indicate in the absolute value bars, these bars here mean determinant, okay, is AD minus BC. So whatever these values are, AD minus BC is to a 2 determinant. Okay, so slightly harder for a 3x3, but the nice thing is the 3x3s use 2x2 techniques. So for a 3x3 matrix B, and here, rather than listing off the first 9 letters, I'll give them subscripts. So A1, A2, A3, B1, B2, B3, C1, C2, C3. So there's your matrix. All right, so what is the determinant of B here? Well, determinant B equals, and remember how it goes here. We're starting off with these A elements, and essentially I'm crossing out the column and the row corresponding to the element I'm working with. In other words, I have A1, and I'm multiplying it by the determinant left over when I cross out. So I put my markers like this, and I cross out those 2 rows. I'm left with a 2x2, this 2x2 down here, and so I care about what its determinant is. And we'll do an example of this in a minute. But it's some constant value times a determinant of a 2x2. And then you got to put some minuses in there. So the same game with A2, crossing out the row, crossing the column out. I'm left with 4 entries. If you do enough of this, you'll get very used to it. Like that. Back to plus again. That should be times. And A3, cross out. You're left with B1, B2, C1, and C2. And you probably imagine that this formula just translates right over to higher dimensions. You just keep alternating signs and doing determinants, and it gets nasty very quickly. But 3x3 case, it's handleable. All right, so why does this matter? Here's why. Let me erase all this, and then we'll do a cross product and see why this is important. So we have 2 vectors, U and U is component-wise, U1i, U2j, U3k, and we have the vector V, and that's V1i plus V2j plus V3k as such. Well, what is the cross product? U cross V is the 3x3 determinant given by the following matrix. So across the top row, we're going to list I, J, and K. And the next 2 rows, we're going to list the coefficients. In other words, this 3x3 matrix has a determinant. That determinant is going to be the cross product. All right. So let's see what this looks like in an example, because it's kind of abstract at this point. All right, so let's make some actual vectors here. So U is 3i minus j minus 2k, and V is I minus j plus 2k. And so my question is, what is U cross V? Okay, so U cross V. All right, well, I need the determinant. I'm going to fill in my entries first of all. I, J, K. The U coefficients are 3, -1, -2. The V coefficients are 1, -1, +2. All right, so remember, how do we do this? Begin with the top left-hand corner entry here, right? And then take the determinant from this matrix down here. So what am I doing? I've got I, and I'm multiplying it by the determinant I would get from just knocking out these numbers and taking what's left over. So what's left over is this 2 by 2 matrix down here in the lower right-hand corner of the screen, and that's multiplied by I. Okay, so this is going to give you some number, some scalar number. This will give you a vector component. Okay, stick a minus in, put your j over here, right? J, cross out the top row and the middle row. You're left with these entries here in a 2 by 2 matrix. All right. Then you go to K, same thing, cross out, cross out. You're left with the lower left-hand corner of this matrix. So 3, -1, 1, -1. Okay? And so what are these determinants? Well, these are 2 by 2, so it's just multiply on the diagonals and then subtract, right? So AD minus BC. So this should be -2 minus +2, which should give us 0. Do I have 0? Yes, I do. Good. So there's 0I. All right. 3 times 2 is 6. Minus a -2 is 8. So this is minus 8j. Remember, the minus is already on the outside there. 3 times -1 is -3. Minus -1, right, is a positive, or is a +1. That's a -2, so it's minus 2k. What do I have here? Yes, it is. All right, good. And so there's your cross product. So your cross product is -8j, -8j minus 2k equals u cross v. And you can see right away it is certainly a vector here. Okay? All right. Next question we can address. So that's how to do cross products. And again, if you do enough of these, they get very natural. Okay. So let's get rid of that. Let's look at finding vectors normal to planes. This will come in very handy in the next section because we want to get equations of planes, right? Then we're going to need these normal vectors to them. Okay, so find a vector normal to the plane determined by the following points, by the points 0, 1, 2. Q gives you 1, 1, -1, and R will be 1, 0, -2. All right? Okay? So, we could put a little picture over here too, I guess. It's sort of tough to plot points in 3 space, but you could do it more or less if you have to. So let's see here. So we'll put R probably somewhere down here. It's 1 on the x-axis and -2 on the z-axis and nothing on the y. And then Q probably go, let's see, so it's 1 and 1 and then -1. So maybe something like that. And P is 0 on the x, 1 on the y, 2 on the z. So maybe it's somewhere maybe up here. All right. We can kind of connect those together. And there's probably your plane, right? What do I have my points labeled? That's R, Q, and that's P. So we want a vector that's perpendicular to that plane. Well, what we know is here are 2 vectors, RQ and QP, and we know that the cross product is normal to both of those. So we know that the vector QP cross QR is normal to both the vectors QP and QR, right? So there's QR, there's QP, 2 vectors. Direction doesn't really matter here because it's a plane, but we know the normal to both of those, so we can use this cross product and get our normal vector. Okay? So let's see here. So QP is what? 0. So going from Q to P is 0 minus 1. This should actually be well, I'll use the I notation. So 0 minus 1I plus 1 minus 1j plus 2 minus negative 1k. All right, so there's your vector QP. And that looks like it gives you negative I and 3k. So there's your vector QP. I'll use black here to denote this. So that's this vector right here. That's QP. All right. Okay. And QR, same way it's gotten. So QR equals, let's see here. So 1 minus 1I and 0 minus 1j plus negative 2 minus negative 1k. All right. Yeah, that's right. And so that gives us 0i and negative j and minus k. Right. Okay. So there's your vector QR. You can put that over here. So, all right, and this is QR. And then the cross product will be at an angle to that plane somehow or another. So your angle is sort of like, kind of hard to see what's going on here, but there's your angle. You're curling counterclockwise, so you're pointing straight up. So maybe your vector is sort of coming out maybe like that. And that would be at a right angle down there and a right angle there. But kind of hard to see what's going on in 3 space, but it's not really that important to see the geometry here. It's more important to see the calculation. But this should be your vector and something like that. Okay. Let's see here. So got to figure out what the cross product is now. So let me erase this, and let's come up here and keep going with this. All right, so we need the cross product. So we need QP cross QR. And again, we'll make our 3 by 3 determinant. Let's see, so we have negative 1, 0, and 3, and 0, negative 1, and 1, like that. Set up our matrices, 0, 3, negative 1, 1, minus j, negative 1, 3, 0, and 1, and plus k, and then that's negative 1, 0, 0, and negative 1, sort of squished over there, but that works. So there's your determinant equation, and if you go through all that, you get, what, 3i, and what have I got here? So that's negative 1 minus 0, so that should be negative 1 minus 0 should be plus j. So negative 1 times 1 minus 0 is negative 1 times a negative is a positive j. That sounds right, yeah. And then over here, positive 1 minus 0 should be a positive k. All right. So there's your cross product. So this vector is normal to the plane determined by P, Q, and R, determined by P, Q, and R. Okay, that's normal there. And what we really want is we'd like to have normally a unit normal vector out of there, like something that has length 1. So the length of QP cross QR, let's just see what it is. What am I doing? Yeah, so QP cross QR, the length of that, well, 3 plus 1 is root 11, right? So if we wanted to, so this vector is normal, but it's not length 1, it's not a unit vector, right? We could take QP cross QR, QP cross QR, and then divide that by square root of 11, and we would get 3 over root 11 I plus 1 over root 11 j plus 1 over root 11 k, and this would be a unit normal vector to the plane. All right, so that would be a unit normal vector. And in fact, generally, when we're discussing cross products, we think about the vector in question as being a unit normal vector, as being a vector of length 1. So this normal to the plane, it's length 1, everything is good there. Okay, so there's our normal vector. Well, what else can we say about this? There's some good geometry here to look at also. So let's take a look at that for a minute. So geometrically, we found that the magnitude or the length, the magnitude of this cross product, QP cross QR, was square root 11, right? That's the length of it, the magnitude. What does this mean geometrically? Well, it's the area of the parallelogram formed by QP and QR. Okay? So when I drew up here before that plane, well, I drew it sort of triangularly, but if we drew it as a parallelogram, as we're used to drawing planes as, sort of, we can see what the geometry means here. Okay? So, in other words, here's two vectors. We'll call them V and U. There's an angle between them, theta, right? And let me actually draw this in dashed here. So if I wanted to finish up the parallelogram here, I could do that, and certainly another copy of V and another copy of U, right? And then we can talk about, so there's U and there's V's arrows, and we can drop this perpendicular here and call that the height. Well, let's look and see what's going on here. So the area of a parallelogram is base times height. So it's base times height. Well, the base of this thing, right, is going to give you what here? So let's see. It's going to be the length of U, right? There's the base parallelogram, so it's going to be the length of U, right? And then the height, well, what's the height going to be? Well, angle theta, this is a right triangle, so we know that sine theta is opposite over hypotenuse. In particular, we'll call this absolute value sine theta. Doesn't matter, this is positive. It's all area, so it's positive numbers. So it would be opposite over hypotenuse, so it's going to be h over square root, or h over length of v, because there is opposite, there's hypotenuse over there, right? Okay? And so we can move that around, and we can say that h equals absolute value sine theta times absolute value of v, right? And so now we have an expression for the height that involves theta and the length of v. So we have this sine theta times length of v as such, right? And so if you recall back to the original definition of what cross product was, remember that cross product, so u cross v is going to be, where are we here? So we got length of u, length of v, sine theta, all times that vector n, right? And so if we put a length around both sides, get the length of that vector, right? However, since n is a unit normal vector, right? Its length is always 1. Its length is 1. So as a consequence, what we have up here then is something like sine theta times that. Well, this is 1, so it goes away. And so what are we left with? We're left with the length of u cross v. So the bottom line is the length for any two vectors u cross v is the area of the parallelogram formed by those two vectors. Okay? So how is this useful? Well, we can find areas of triangles very easily this way. So let's look at an example. So I kind of switched over there from talking about QP and QR to general U and V. That's fine. Let's go back to QP and QR for a minute. So let's find the area of the triangle shown below. And so I will use actually the exact same triangle we had before. Let me push it further down, give us more room here. So here's P, which was that point 0, 1, 2. It's going to bump itself down to get to Q, 1, 0, negative 2. There's Q. And then go over here to R, 1, 1, negative 1, something like that. Right? So this is the same triangle we had in the previous example. Right? I think I called this point, let's see here. So I called that point Q. This point should be 1, negative 1, and this point should be 1, 0, negative 2. Makes a big difference. So I want to know what's the area of this triangle. All right? Well, think about it like this. We already know what the magnitude of the cross product is in this case for QP and QR. Right? So we know magnitude of QP cross QR is square root 11 from the previous example. Now, this gives us the area of a parallelogram, which means I would have to fill in these couple sides here. Let's make this look parallel here, right? So if I filled in those couple sides, right, then the area of this parallelogram is square root 11, right? And notice here, let me put in the sides here. So this is QR down here. Let's see here. This is PR over here. Over here we have another copy of PR. And let's see here. Then up here we have a copy of a QR, right? So that parallelogram, right, has area square root 11. Well, the triangle in question is half of this parallelogram, right? This parallelogram is just two copies of the same triangle. So the triangle in question has 1/2 the area of the parallelogram. So area of triangle is root 11 over 2. Right? So again, parallelogram has area of root 11. Triangle is half that. Area of the triangle is root 11 over 2. Okay, so let's shift gears slightly here. Let me get rid of this stuff. And we'll move to a new topic still involving cross products. This is called the triple scalar product. Triple scalar product. Okay, so I've got U cross V dot W is what we refer to as the triple scalar product of vectors U, V, W. All right, so involves both a cross product and a dot product. Perfectly fine. u cross v gives us one vector, and we're dotting that with another vector. So eventually this will be a scalar, as the name implies, because at the end you have a dot product that's going to give you a scalar out. Okay? It's also called the box product. Box product. The reason being because its volume, or its length, I'm sorry, also gives you something very useful. So if you look at the length of this vector here, right, it gives the volume of a parallelepiped. Let's see, parallelepiped. Yeah, there you go. That looks good. All right, parallelepiped, which is a parallelogram sided box determined by u, v, and w. Okay? So this thing gives the volume of this parallelogram sided box determined by u, v, and w. All right. Well, what does this mean here? Let's take a look at it for a minute. So let me get rid of this, and then we'll look at what these things even look like from the geometry side of things. So here's, all right, so let me draw a base here. So here's u, and here's v, all right? And then I wonder, let's see here. We'll kind of try to make these dark looking. All right, there you go. And then you've also got another side over here, parallel, and you've got sort of this back end here, all right? And then, let's see, what's going on now? So then you've got another parallelogram running, let's see, so something like that, and like that. It's not going to turn out right. Well, let me draw this more in the center of the board here. That would look better, I think. So let's try this again here in the center. All right, so there's u. There's v. All right. We got this sort of backside here. Then you've got something that looks like that. And we could probably make this, let's see here. How about that? Is that going to look any good? Yeah, it's not terrible looking. So let's see. Let's try to keep drawing this thing here. And we get something that looks like that. And so we can sort of like that. And then the last side will be, so this is going to look like, so here's W. All right, let's connect all this together and make this look pretty. Okay, so I've seen worse, but so okay. So where are our vectors here that are important to us? So here's vector v. In fact, let me highlight the vectors we care about in black. So here's vector u. All right, so there's u. Here is vector v. All right, and vector w is out here. So here's w. Here's v. Here's u. There is our parallelepiped. Parallelepiped determined by u, v, and w, okay? And so I want to figure out what the volume of this thing is. I like it to be the triple scalar product's absolute value. So the volume of this box is length times width times height. Well, length times width is the area of this base down here, right? So this is actually, so let's put an equals here. So this is actually the area of the base times height. And that's great because the base doesn't look right here. I see what's going on. So let's make this so, how about that? And then push this up here. And good enough. All right, so the area of the base is the area of the plane formed by U and V down here. And so that area is the length of U and V's cross product. In other words, this base down here, these four sides down here, they form, this parallelogram down here, its area is the length of U cross V. Okay? And now, what about the height? Well, be a little bit careful here. So if we come over here, the height is going to be there. And remember, we can drop a perpendicular from W over to the height, right? And when we do that, so this is a right angle. When we do that, that screams to us vector projection, right? Dropping perpendicular from one vector to another screams vector projection. And in particular, this vector over here is the projection of U cross W, U cross V, W. So it is the vector projection of W on to U cross V, since U cross V is orthogonal to both U and V, correct? So this is a right angle down here. This height here is coming up at a right angle to this parallelogram down here, this base parallelogram, U and V. And so we are projecting W onto the vector U cross V. That vector, I don't see it anywhere up here. It's not up here at all because I don't know how far it is and how long it goes for. But what I do know is that it goes in the same direction as this height vector does. Okay? And so then we have some angle, theta, which is there, right? We have a right triangle, right? Cosine theta, right? Absolute value of that equals the absolute value of the height, which is, let's see here, so that would be, right, okay. So would be h adjacent over hypotenuse would be h over absolute value w, right, like that. And so what does that end up giving us here? Well, if we want to figure out what h is, that means h is equal to w cosine theta, like that. So this is an expression for the height here. It is the length of this vector w times cosine of this theta here, between this projection and w vector, okay? So we have an expression for h, cosine theta, all right? And then think back a minute here, get rid of this. Remember, we had an expression involving cosine and the dot product, right? So cosine theta was equal to a dot b over the length of A times the length of B, right? Well, what is our cosine theta up here? What are our A and our B? Our A and our B are W and U cross V, right? So in our case, we have absolute value cosine theta equals U cross V dot W, right? Because the vectors involved here are W and U cross V, right, the projection there, over the length of U cross V times the length of W as such. And so this thing is equal to this, right? Let me come over here. So what do we have now? We have volume equals U cross V times W times length of W times length of U cross V times W over length of U cross V length of W. So we have this big expression over here now that's been subbed in for the cosine. And what happens here? Well, we can cancel that, all right? Cancel that. Those are scalars. And what are we left with? The absolute value of a triple scalar product as our volume. So this is what a parallel pipette looks like, and this is why its volume is equal to that. Okay, so that's all well and good. How do we use the thing, though? So I'm not going to derive this, but the formula that we care about is the following. Let me clean this up here. So we care about how to use it in practice. So here's triple scalar product. It is the determinant U2, U2, U3, V1, V2, V3, W1, W2, W3. It is that 3 by 3 determinant here that we care about. And again, notice there's no I, J, and K across the top here. This is a scalar, not a vector. All right? So let's do an example. So find the volume of the parallelepiped determined by the following vectors. U is equal to 3I plus J. V is equal to negative I minus 2J plus K. And W is equal, look at W. W is equal to J plus K. Okay? So we're doing a 3 by 3 determinant here. U cross V dot W is equal to, fill in the coefficients, 3, 1, 0, 1, negative 2, 1, 0, 1, 1. That's what I've got. And then crank this thing out. You've got 3 times this 2 by 2 determinant. Hopefully by this point you're getting comfortable with doing these. They're not so very terrible. 1, 1, 0, 1. And plus, and the nice thing about the last one is it just zeroes out. So it doesn't matter what's over here. It's gone anyway. Okay? So you do that, right? You have 2 2 by 2s to deal with. So you've got negative 2 times 1 is negative 2. Minus 1 is negative 3. So this should give you a negative 9. Negative 9 down there. 1 times 1 is 1. Plus 0 is 0. So you should have a minus. Let's see here. So 1 times 1 is 1. Yeah. So you should have a minus 1 here. And that should give you a negative 10. All right. And so the volume is 10 cubic units. Again, volume is a quantity that must be positive, therefore we have to take the positive of this. It's negative 10 is the actual triple scalar product, but the volume is 10 cubic units. Okay, that is it for the cross product.